Hello and welcome. I'm Chris Murphy, and in this video, I'm going to cover how to calculate an image distance using a thin lens formula. Although the goal of this video is to have you calculate the image distance using the thin lens formula, this equation can be used to calculate object distance as well as the focal length. Additionally, even though it's called the thin lens formula, this equation can be used to do calculations for spherical mirrors as well. So in this equation, f is your focal length, dO is your object distance, and dI is your image distance. And most important, when applying this equation, is using the right signs for the object, the image, and the focal length. For example, the object distance, if it's positive, that means that your object is on the same side as the incoming light. And that scenario would look something like this, where both our object and that incoming light are on the left side of this lens. Now, in some situations, you might have the object located on the opposite side from where your light is incoming. This is really going to only apply if you have a multi-lens or a multi-mirror system. Otherwise, if there's just one lens or one mirror, object distance is always going to be positive. Now, for the image distance, if it's positive, that means it's real. And what it means to be a real image is that your light rays really converge where your image is formed. So in this example with the lens, we see that the light rays are converging right there. That tells us that that image formed is a real image. Now contrast that with an image distance when it's negative. That means that it's going to be a virtual image. In this case, the light rays don't really converge there. At this point right here, we have to trace the rays back to get to our image. So again, if the light rays really converge, you have a real image, and it's positive. If you have to trace the rays back and they don't really converge, that means it's going to be a negative image distance and be virtual. It may also help to remember that IR and UV always go together. IR meaning inverted and real, and then UV meaning upright and virtual. So every inverted image is a real image. Every upright image is going to be a virtual image. Now let's apply that equation to a couple scenarios. Here you have a student places an object 20 centimeters in front of a converging mirror with a focal length of 10 centimeters. And we're asked to find where the image is formed and whether or not it's real or virtual. So to do the calculation, you're going to have to use our thin lens equation. So we have 1 over focal length is equal to 1 over the image distance plus 1 over the object's distance. And now we can start to plug things in. Focal length is going to be 10 centimeters, and notice it's converging. That's important, because if it said diverging, it would be a negative 10. Converging systems always have a positive focal length. The image distance is what we're trying to calculate, and the object distance is going to be 20 centimeters. So we need a common denominator. That's going to get us 2 over 20. We'll subtract 1 over 20, and that's going to calculate 1 over the image's distance. So we're left with 1 over 20 is equal to 1 over the image distance. So lastly, to find the actual distance where our object is formed, we just do the reciprocal of that. So our image's distance is going to be 20 centimeters from the mirror. Now to determine if it's real or virtual, all you have to do is look at the sign. This is a positive 20, which means it's going to be real. Now for a little bit more practice with the second question. This time we have an object 50 centimeters in front of a converging lens, but we're given power of 1 diopter. We still want to find where the image is found and whether or not that image is real or virtual. To start off with this one, you'll need to remember that power is equal to 1 over the focal length, and it's in units of 1 over meters. So if a 1 diopter would be 1 over 1 meter. And we can combine that with our thin lens equation of 1 over the focal length is equal to 1 over the image distance plus 1 over the object distance. From here we can take that power of 1 over 1 meter, which again is same as 1 over the focal length, set that equal to 1 over our image distance plus 1 over our object distance. And you may have already noticed that we have a difference in units. The object is given as 50 centimeters, and we have power as 1 over a meter. So let's change our meter into 100 centimeters. and then we have 1 over our image distance, plus 1 over our object distance of 50 centimeters. Now you can solve for the image distance. We'll have 1 over 100 centimeters is equal to 1 over the image distance, and we're going to convert this to have the same common denominator of 100. Now we have 1 over our image distance is equal to 1 over 100 minus 2 over 100. And when you simplify that a little further, we're going to have 1 over our image distance is equal to negative 1 over 100. That tells you then that the image distance is at negative 100 centimeters. And again, the sign is really important here. The negative sign tells you that this is going to be a virtual image. So to sum everything up, remember that the thin lens formula can be used to calculate focal lengths, image distance, and object distance. And the most crucial part is making sure that the signs are correct when you plug in those numbers.